All right, hello everyone. I'm Camille Owens. I'm going to be talking about how to build efficient web scrapers and kind of how you leverage Python and Rust for data ingestion. So a little bit about myself. I've been in the tech industry for about 7 years now. I got a degree in computer science from the University of Colorado Boulder. And when I graduated, I actually wasn't super sure what field I wanted to go into. And because I had done a mixture of software and hardware projects, I kind of wanted to do DevOps for that reason. So I did that for about 3.5 years. I worked in the telecommunications sector. And then after that, I actually wanted to write a bit more code. So I went into software engineering in the startup sector. I worked for a company called Odermark. They worked with the food service industry. And then after that, I worked for a company called Tomorrow.io, where I currently work. They work on building out weather intelligence systems. And I've done a lot of work with Python and Rust data ingestion. So relevant to today's topic. So let's dive into it. Do you want to use a web scraper or an API call? Well, for starters, what is a web scraper? It's a tool or script that automatically extracts data from websites, usually by navigating HTML, parsing content, and collecting specific elements like text, images, or links. And then an API call is a direct request to a server that returns structured data, usually in JSON or XML, and it's defined through an endpoint. It's a real clean and efficient way to get data when it's available. However, APIs are limited. They come with rate limits, restricted access, missing data fields, or they just simply don't exist for the content that you need. And you might even need to apply for access or even pay for higher tiers. So scraping is generally required when there is no API, right? The API is too limited, or the site shows content dynamically that isn't exposed otherwise. So scraping becomes the fallback for accessing publicly visible data. So some examples of cases for scraping are, it automates data collection, right? Manually collecting data is slow and error prone. Scrapers can collect thousands of entries in minutes, especially useful for dynamic or frequently updated data sets like weather, prices, or social media. And then it tracks changes over time. It enables longitudinal studies. So you can capture how data evolves daily, weekly. It's really critical for trend analysis, forecasting, and time series modeling. And you can have, access hard to find data. Not all valuable data is easily accessible. Scraping helps pull information from government sites, NGO pages, or legacy systems. And it can unlock that gray literature as well. And then you can also collect publication metadata. You can automatically pull DOIs, abstracts, authors, citations. It can really speed up that literature review. And then it really enables open science. Scrapers can be shared and reused across research teams. It promotes reproducibility and transparency. And you can also help automate tedious tasks so researchers or engineers can focus on insights. So what language do you want to write this in? Well, I'm going to compare Python and Rust and their principles and just kind of do a little overview of that. So with Python, right, you generally hear, simple is better than complex. Python's design policy really shines in the web scraping tasks, especially for quick scripts and experimentation. It really encourages clear, straightforward solutions, which is great when you're dealing with messy HTML. Makes it a lot easier. And then you really want it to be readable, right? The code should be easy to read, even for newcomers. This makes collaboration and debugging much easier. It lets you prototype and iterate quickly without much boilerplate, and it's really perfect for exploratory scraping or one-off scripts. And that given Python is dynamically typed, it means fewer rules, faster development, but there's a lot more room for runtime errors, so testing is really crucial. So, overall Python prioritizes developer speed and clarity, which is why it's the go-to for many scraping projects. So why would you use Rust? Python sounds pretty good so far. It takes a very different approach from Python. It prioritizes safety and performance without compromise. One of its core strengths is memory safety by design. Through ownership, borrowing, and lifetimes, Rust prevents entire classes of bugs like null pointers and data races before your code even runs. It's very performance focused. Rust compiles down to highly optimized machine code, and then, thanks to zero cost abstraction. So, which are, you can use high level features like iterators or generics without incurring any runtime performance penalty compared to writing low level code. And even though this feels super strict, right, the compiler is unforgiving, but that's a really good thing. It enforces correctness at compile time, which drastically reduces unexpected runtime behavior, which I have noticed like within a working environment has been really great. So the trade-off is, Rust does take longer to learn, but the payoff is a fast, reliable, and bug-resistant scraper. And this is really important when you're deploying your application, your code to a production environment, and especially if you need it to scale. So with scaling, you want to try and make it asynchronous if you can. So what is the difference between a synchronous and asynchronous system? Well, a synchronous one are when the tasks are executed one after another, and then with each task starting only after the previous one completes. So this is really great for small jobs, but it's really not great if you're trying to scale this. And then with an asynchronous one, it lets multiple tasks run in parallel. You can fetch one page while pausing another or waiting from a response from a third. So this really matters, right, when you're dealing with thousands of requests. If each one waits its turn, the process is going to crawl. So, blocking operations can be such a waste of time and memory, especially when most time is spent, waiting on network responses. So this is really essential for high volume pipelines. You need to keep up with real-time data, and that means speed. So really, efficient concurrency means faster ingestion. If it's running in the cloud, that's less cloud spending, and then you have more reliable pipelines. So how would you go about that with Python and Rust? Well, Python makes it pretty easy, right? You can use libraries like Asyncio. It's a single-threaded event loop for asynchronous tasks. And then you can use libraries like AIO HTTP, where you can fire off many HTTP requests at once. But there is a catch, the GIL, so the global interpreter lock, where this only allows you only one thread to execute Python bytecode at a time. And this really limits true parallelism in multi-threaded programs, and it really limits scalability. So even though Python's really great for input, outbound, bound tasks, like downloading web pages, but if it's CPU heavy, Python can quickly become a bottleneck. And then with Rust, right, it offers native async await with real multi-threading. It's powered by crates like Request and Tokyo, and that scales across the cores, so you have no GIL to hold you back. So, Rust really enforces memory concurrency safety at compile time. So you get that performance and reliability. And it's ideal for input, outbound, heavy, and CPU-intensive scraping pipelines, especially when efficiency matters. So I kind of mentioned two crates there. I'm going to kind of go over that real quick. So, what is Request? Well, Request is a high-level HTTP client library used to make asynchronous or blocking web requests easily and safely. It's native, it has async await support for non-blocking HTTP pulls. It has built-in timeouts, connection pooling, automatic redirects. It supports both HTTP 1.1 and 2, so it's designed to handle many simultaneous requests without blocking. You can handle retries and failures really gracefully, and you can stream responses efficiently. So, it's really great for large files. So why this is great for scraping? Thousands of concurrent requests, integrates seamlessly with the Tokyo runtime, which I'll go over in a sec. And then you have low memory overhead with high throughput, and then, it's safer by design, right? Avoid silent failures or crashes. So here I have an example on the right here, really, really simple. You're just like, you have an asynchronous GET request to the GitHub API. You wait for us to wait for the HTTP REST to finish. You have the try operator that's used to propagate errors and functions and return the result or option. Then you kind of want to bring in here, the error type into scope so we can use the function. So yeah. And then with Tokyo, this is a high performance asynchronous runtime for us. So it's similar to Python's Asyncio, but it's designed for true multi-threading and scalability. So it enables Rust async await functionality by efficiently managing lightweight, non-blocking tasks. As a foundation for many networked applications in Rust, Tokyo powers libraries like Request, which relies on it to handle non-blocking HTTP operations. Gotta be honest, I've used Tokyo for every app I've used at work, so it's super useful. So its core capabilities are task scheduling with low overhead, native support for timers, sleep, async input, outbound. It integrates tightly with request, hyper, and async file systems, and it's optimized for multi-threaded execution. And then this works really well because it uses work stealing and it has cooperative scheduling to keep threads balanced, and then enables thousands of concurrent tasks without blocking, and then efficient. It's really efficient even under high retry reconnect load. So if you have an unstable source, you want to make sure you're retrying that. And then it has built-in tools for monitoring, throttling, and control. So we kind of have an example on the right here, right? There's 2 tasks that are being run. Task 2 finishes before task 1, but we just use a join macro provided by Tokyo in the async runtime that allows you to run multiple asynchronous tasks concurrently and then wait for them all to complete. So kind of an example here, right? Like very simple, but you can kind of see how that kind of works, where if you have multiple tasks you're trying to run, they don't have to finish at the same time. So talked a lot about like some of those libraries and the principles, like how do you go about parsing this data, especially when you have raw, messy HTML and that's really inconsistent. It's not structured for direct use. So with scraping, it means navigating the DOM, not just downloading text. And so, there are some really great HTML parsing libraries in Python. I'm sure you've heard of, Beautiful Soup. That's really easy to use. It's a forgiving HTML parser. LXML, it's fast, it supports XPath and CSS selectors. This HTML5 lib is robust but slower, and it replicates how browsers parse. And then with Rust, you have Scraper. That's a CSS selector-based one inspired by jQuery. And then Select, which is fast and minimal, and it's good for simple trees. With Rust, and this pops up a lot, is that the ecosystem is less mature compared to other languages. So there is sometimes some difficulty there because Python just has so much more. It's been around longer. So kind of some real world examples of like where you maybe want to use this, right? If you want to extract tabular data from NOAA dashboards and convert them into structured JSON alert objects for easier downstream processing and integration. If you want to parse file strings like from an FTP server, apply filters based on naming, patterns, timestamps, or region. Another one is like you want to ingest raw meter aviation weather data. So like that's like a concise report of current weather conditions at an airport. So like you want to transform them into standardized structured objects representing temperature, wind, visibility, or other weather attributes. So the thing is, especially like in the weather industry, right? There's a lot of different scientific formats, and it's not always going to be like HTML or JSON. So they come in a lot of binary formats. So for example, I deal with a lot of formats like GRIB, which is a compact binary format for weather forecast. And then I also use netcdf, which is a portable format for multidimensional scientific data. And then HDF5, which is a scalable format for storing large, complex data sets across many scientific fields. So, ingestion pipelines must read, stream, and sometimes parse these files. Python is the best for this. It has the best in-class ecosystem for, GRIB and netcdf. So, there's a lot of libraries like cfgrib, Xray, netcdf4, and it makes parsing and analysis a lot easier. And, it supports slicing, metadata extraction, compression, and even plotting. So this is really ideal for exploratory work and format decoding. Rust really lacks in this area. It lacks native support for parsing scientific formats. There are very limited crates for netcdf or HDF5. You can use bindings, and I know that's like a topic for another time, but that can get quite complicated and doesn't always make it super easy. So the strengths really lie in streaming, downloading, and cloud transfer. So, often used to ingest and then pre-process data before handing it off to Python. I ran into this recently. I had a library I had to use for certain like satellite imagery. I tried to use it in Rust, but their library was in Python. So you do kind of run into that issue a lot. So here are just kind of some examples where you would kind of use both, right? So like with the NOAA GRIB forecast, you would scrape that with Rust, or with Python, sorry, and then you would stream that to the cloud storage with Rust. Or you'd have satellite imagery metadata extracted and from netcdf files. So you probably grab the files with Rust, but then extract all that metadata with Python. And then, for example, if you have FTP pipelines that, you copy that over with Rust, and then you'd batch the code formats using Xray using Python. So it'd be kind of a way to leverage both here. So now that you've scraped a lot of data and you've kind of, done all that, and you have all your data that you need, you're probably going to have a pretty large tabular data set, like with your CSVs, JSON, or your structured HTML tables. And a lot of the times you're going to need some kind of data frame library to kind of figure that all out, because you want to be able to parse, filter, and transform. So, and you want to be able to scale, right? With limited performance in this stage, it becomes a major bottleneck in the pipeline. So I'm sure a lot of you have heard of pandas, right? It's, been widely adopted. It's used in a lot of different industry. It's, flexible. It has an intuitive API, has a pretty rich ecosystem. It integrates well with a lot of libraries, but it is slow with large data sets because it operates in memory only. So if that data exceeds the available memory, it may crash or slow down drastically, which can be quite frustrating. And then with Polars, which is Rust's version of pandas, it has, it's fast, it's multi-threaded. It has lazy and eager execution, which lazy execution delays computation until the result is needed. So saving resources by avoiding unnecessary work. Eager execution runs computations immediately, which makes debugging easier, but can use more memory and time if results aren't needed. So this goes, well with large data sets, even on limited machines. However, kind of with a lot of things with Rust, right? It still has a growing ecosystem. It integrates well with like Arrow, Parquet, but and some streaming sources, but not all the time. So sometimes you do have to find kind of some support to get that working. So I'm just going to show you like a small code example in Rust about how you can use some of the Noah forecast script ingestion and how you kind of go about that a little bit. So let me know if you can still see my screen.
It's fine for me. I'm on a giant screen, so.
Okay, do I need to zoom in at all?
Could you zoom a tiny bit, Camille?
Yes. Is that better or a little bit more?
Yeah, that's okay.
That's better.
I'll do one more. There you go. There we go. Okay, so here, you're trying to ingest some data from, so we're using a GFS data, so it's a global forecast system, and we have our grid files from NOAA. We have the URL here. We also have all our crates here that we're importing. So we're using request here in Tokyo. So you're making sure this is all asynchronous. And I will get into futures in a sec. But here, right, we've defined our URL. We have the date, which this was yesterday's date. So we can, I'll just leave it. We can update it if we want to. With the data we're trying to retrieve, they are run in 6-hour cycles. So, midnight, 6 a.m., 12 p.m., 6 p.m. Also, everything's done in UTC time. So just in case you guys were wondering. And then we want to make sure we create, an HTTP client instance. And then we've created that. And then we want to generate forecast hours. So they run every 3 hours. So the data is uploaded every 6 hours, but they have files that run every 3. So that's just part of the upload. So we want to make sure we're iterating through that. And then I've also declared futures in here. So future is an asynchronous computation that produces a value later. Think of it kind of like a promise or a task. It does nothing until it's awaited. So once awaited, it runs until it's ready. So like a file downloaded or a network response is received. And then futures unordered is a concurrent task queue from the futures crate that runs many futures at the same time. It yields their results as soon as each one finishes, not in order. Kind of think of futures unordered like a task pool, essentially. So you just drop a bunch of async tasks, and it lets them all run. So that's kind of what we're using that here, because we want this to run asynchronously and we don't care when it comes in. So we want to loop through each forecast hour. So we just have like a vector of strings here. It's only 3 files, but sometimes that can become quite large. So you want to set that maybe up a little differently. Then we want to format our URLs, like what we're trying to grab, the files we're trying to get. So you can see here, we have the URL, right? So we have the date, the cycle again, and then the files that we need. So we kind of have to build that up. These can get so long sometimes. So you just got to make sure, you want to make sure you're logging that and formatting that accordingly so you haven't missed anything. So, and then you want to make sure that you clone your client, because we're running this asynchronously. We want each of our tasks to run individually, right? Because let's say one does finish before the other one. You want to make sure, it's able to run just fine. So, and then before I get into this, we're going to download our file here. So we have this function down here. We want to pass our client, our URL, and our file name, like whatever you want to save it to. And then we have, here, right, the response where we're setting this up here. We want to send that GET request and convert any error that we get into. But this line sends an HTTP GET request given the URL using the client, and then it adds custom user agent headers, and it waits the response and converts any network error into a standard input outbound error to match the function's error type. So this can be really great. This actually be a lot longer. Like if you have user credentials, you'd add it here and you can set it up however you like. So, and then we just want to make sure we got a response right. We want to make sure it was a 200 response and nothing else, because otherwise we don't want this to keep running, right? And then, you open the file for writing, convert the response body into a stream of byte chunks, and then you write each chunk to the file as it arrives. So going back up here with this, so this code adds a new async toss to the futures queue, and then it downloads a file from the given URL and logs, whether the download is successful or has failed. So we have our match statement here, right? You could rewrite this and just say like it's an if else statement, right? Like if this is good, return that. If not, error, right? So that's all that's kind of doing here. And then down here with this line, we have a line that, it waits for each async task in the futures unordered queue to finish. So one by one, and it loops until all the tasks have completed. So the thing is too with like ingestion, a lot of the times your files, whatever you're using, whether it's like the cloud or your local machine, or if you're downloading them, but generally like files will sort numerically and lexicographically. So it'll be in the correct order. So kind of how you see here, right? Like where it's downloaded. And you see how like when it got saved, right? It wasn't in order. So it just whatever downloaded first and was faster. So this can be really great and can save you so much time when you're adjusting so much data. So yeah. When do you want to use Python or Rust? Like which one should use? How do you go about that? So with Python, when you need to quickly prototype or iterate on ideas, when you're working with scientific formats, like GRIB, for example, and then you have that flexibility and ease of development that matter more than the raw performance, or you need to integrate that with, data analysis, plotting, or like if you use Jupyter notebooks, and then the parsing is complex with HTML, so you want to use robust libraries. And then with Rust, you want it to use it right when you need performance and memory efficiency, and that's really critical. So if you're streaming like 10,000 plus files, right, you're probably going to want to use Rust. And then you really need true async concurrency, so 1,000 simultaneous HTTP requests. And then if you're building production grade ingestion pipelines with high reliability. So if you have a client, right, and you're building this out and they're getting that data, it would probably be best to write it in Rust for that reason. And if you're deploying to resource constrained environments, and if you want, compile time safety guarantees and zero cost abstractions. So really, you kind of want to do a hybrid of the two. You want to use Rust to download, stream, and transport large data volumes, use Python to parse, analyze, and visualize structured data. And then you might, connect them via like file systems. So, Rust writes data to a disk and then Python reads it later. It's simple and reliable, but it's not real time. If you're using cloud buckets, so, Rust uploads data to cloud storage like AWS S3 or DCS or Azure Blob, and then Python can pull it there. That's really good for distributed workflows or large data that isn't fit on one machine. It's generally the more popular choice for using that. Or you can use inter-process APIs. So that's a way, inter-process APIs are referred to ways like two separate programs or processes running on the same or different machine, and they can communicate and exchange data in real time. So Rust and Python run as separate processes, but communicate through API sockets and shared memory. So an example of that would be, Rust runs a local web server and sends data through a pipe. Python connects and reads directly from it. So yeah, thank you.